Semigroups and their representations, Lecture 15, Problem Session. Problem 1. Let S be the semigroup with two elements A and B, and with the operation defined by x times y is equal to x for all x and y in S. Write down explicitly the transformations with which the elements of S act in the left regular way on S upper 1. Solution. Let us look at the semigroup S upper 1. The semigroup S doesn't have any unit element, so S upper 1 is S with the unit element 1 adjoint. So it has three elements, 1, A, and B. The Cayley table of S upper 1 is as follows. So 1 times 1 is 1, 1 times A is A, 1 times B is B, A times anything is A, and B times anything is B. And from this we have the following transformations which define the left regular action of A and B on S upper 1. So the action of A sends all elements of S upper 1 to A, and the action of B sends all elements of S upper 1 to B. So this is just the action of A is the second row of the Cayley table, and the action of B is the third row. That's because in the left regular act, the action is given by left multiplication. This completes problem 1. Problem 2. Classify all transitive acts by total transformations over the semigroup S from problem 1. So to start with, we have the trivial singleton act, which consists of one element, that's a singleton, and on this element all elements of X act as the identity. Next, let us note that the left regular S act S is transitive. Indeed, A times B is A, and B times A is B. So starting from any element and multiplying with a different element, we go to the other element. And this implies the transitivity of the left regular S act on S. And now we claim that up to isomorphism, these two transitive acts are all. Indeed, let Q be a transitive S act and let X be an element of Q. Then the set A applied to X and B applied to X is S invariant for obvious reasons, and hence coincides with the whole of Q by transitivity. If A applied to X is equal to B applied to X, that set is a singleton and we get the trivial singleton act. Otherwise, if these two elements are different, we have two elements, that's as many as in the semigroup S, and so we will get the left regular act. And this completes problem 2. Problem 3. Let S be the semigroup from problem 1. Show that any transitive partial S act is, in fact, an act by total transformations. Solution. Let Q be a transitive partial S act and X an element in Q. Assume that X is such an element that it belongs to the domain of the element A. Let Y be A applied to X. Since A squared is equal to A, Y must be in the domain of A, and A applied to Y is equal to Y. Since AB is equal to A and B squared is equal to B, it follows that Y is in the domain of both A and B, and A applied to B applied to Y is equal to Y, and B applied to B applied to Y is equal to B applied to Y. In other words, the elements Y and B applied to Y form an S-invariant subsets of Q, and since Q is transitive, it follows that this set coincides with Q. Moreover, we see that both Y and B applied to Y belong to the domains of both A and B, and so this act given by these two elements is an act by total transformations. That completes the proof. Problem 4. Prove that every finite semigroup has only finitely many transitive acts up to isomorphism. Solution. Let S be a finite semigroup. Let Q be a transitive S act. Consider the monoid S upper 1 associated with S. Note that S upper 1 is finite as well, because S is finite and we, in the worst case scenario, add one extra element. Letting the identity 1 act as the identity element of Q, we turn Q into a transitive S upper 1 act. Conversely, any transitive S upper 1 act is also a transitive S act. Indeed, let R be a transitive S upper 1 act. Since S upper 1 is finite, we have that R is finite as well. Assume that R as an S act is not transitive. Since R is finite, it definitely has a non-empty S invariant subset R' that is minimal with respect to inclusions. Then, of course, R' is S1 invariant subset as well, because the only difference is the identity element which acts as the identity. It cannot move us outside of R'. So in particular, we get R is equal to R' due to transitivity, and this shows that R is also transitive as an S act. We can sum this up. There is a bijection between transitive S acts up to isomorphism and transitive S1 acts up to isomorphism. And this means that it is enough to solve the original problem under the assumption that our S is a monoid. So now assume that S is a monoid and Q a transitive S act. Pick some element X in Q and consider the map from S to Q, which sends an element A in S to A applied to X. Let's denote this map by phi. Note that AB is sent to AB applied to X, which is equal to A applied to B applied to X for all AB in S. And this means that our map phi is a homomorphism from the left regular S act S to Q. And this homomorphism is surjective since Q is transitive. The image of this homomorphism is obviously an S invariant subset of Q. And to sum up, each transitive S act is a quotient of the left regular S act. Since S is finite, the left regular S act has only finitely many quotients, and this completes the problem. Problem 5. Let S be a monoid with identity E. Let Q be a semigroup, but not necessarily a monoid act over S. Let Q upper E be the set of all elements X in Q, which are fixed by E, so E times X is equal to X. A. Show that Q upper E is S invariant. B. Show that every element of S maps Q to Q upper E. And finally C. Show that the action of S on Q can be determined in terms of the action of S on Q upper E and the action of E on Q. Solution. Let X be an element in Q upper E and A an element in S. Then E applied to A applied to X is equal to EA applied to X, and this is equal to A applied to X since E is the identity. Hence A applied to X belongs to Q upper E, and this proves A. Furthermore, the same computation actually works for any X in Q and A in S. Indeed, E applied to A applied to X is equal to EA applied to X, which is equal to A applied to X, which means that A applied to X belongs to Q upper E, and this proves B. So in particular, it follows that E maps Q to Q upper E. Now for any element A in S and X in Q, we have that A applied to X is equal to AE applied to X, and this is equal to A applied E applied to X. And this means that for A in S and X in Q, we have the following. A applied to x is equal to A applied to x if x is in Q upper E. Otherwise, A applied to x is equal to A applied to E applied to x if x belongs to Q minus Q upper E. And here let us note that E applied to x is now in Q upper E. So indeed the action of any A on any x in Q is fully determined by the action of A on Q upper E and the action of E on Q. This proves C. Problem 6. Describe explicitly the action of the elements of IS2 on all transitive partial IS2 acts. Solution. The monoid IS2 has 7 elements. We have 4 elements of rank 1, the element pi1, which is defined on 1 and sends it to 1, the element pi2, which is defined on 2 and sends it to 2, the element tau1, which is defined on 1 and sends it to 2, and the element tau2, which is defined on 2 and sends it to 1. And we also have 2 elements of rank 2 and 1 element of rank 0. The element of rank 0 is the map with empty domain, and the elements of rank 2 are the identity element E, which sends 1 to 1 and 2 to 2, and the elementary transposition S, which swaps 1 and 2. So we have 3 two-sided cells, the two-sided cell J2 consisting of the 2 elements of rank 2, the two-sided cell J1 consisting of 4 elements of rank 1, and the two-sided cell J0 consisting of the unique element of rank 0. So let us now go through all transitive partial IS2 acts for each apex. So each partial transitive act has an apex, and this apex is a J cell. So we have 3 possibilities for this apex. Let's go through all of them. We start with the apex J0. It contains a unique idempotent, which is 0, and the H-class of this idempotent is a singleton, and so it's a trivial singleton group. So this has a unique subgroup, namely the group itself, and therefore, so since our transitive acts with a given apex are indexed by conjugacy classes of subgroups in any group H class of this apex, we have a unique transitive partial act with this apex, and then it must be the cell act. So the left class of 0 is a singleton still and consists of the 0 element of IS2, and all elements times the 0 element give you 0, so the corresponding cell partial act is just the trivial singleton IS2 act. So it has 1 element and all elements act on it as the identity map. So in fact that's an act by total transformations. Next now let's move to the apex J1. J1 has an idempotent pi1, and the H class of pi1 is a singleton and hence is the trivial singleton group. It has a unique subgroup itself, and so there is a unique transitive partial act with this apex, namely the cell act. So the cell act is constructed on the left class. The left class of pi1 consists of pi1 and tau1. So that's the underlying set of our cell act. The element 0 acts on this act as a map with the empty domain, as a map which is nowhere defined. And of course the element E acts as the identity. The element S, its multiplication with pi1 goes to tau1 and back, so it swaps pi1 and tau1. So since pi1 times pi1 is pi1 and pi1 times tau1 is 0, the domain of pi1 on our act is pi1, and pi1 is the identity on this domain. Since tau1 times pi1 is tau1, and tau1 times tau1 is 0, the domain of tau1 on our cell act is pi1, and tau1 sends pi1 to tau1. Next, since pi2 times pi1 is 0, and pi2 times tau1 is tau1, the domain of pi2 on our cell act is tau1, and pi2 sends this tau1 to tau1. And since tau2 times pi1 is 0 and tau2 times tau1 is pi1, the domain of tau2 is tau1 on our cell act, and tau2 sends tau1 to pi1. And this completes the description of our cell partial act with apex J1. Finally, we can consider the apex J2. So it contains the unique idempotent E, and the H-class of this idempotent is the symmetric group S2, with two elements, E and S. And this group has two subgroups, namely S2 and E. And these subgroups are not conjugated because they have different cardinalities. Therefore, we have two different transitive partial acts with apex J2. The first one is the cell act, which always exists. So the left cell of E is our group S2, and we can identify it with S2 modulo the trivial subgroup. And this is the underlying set of our act. All elements outside S2 act on this act as the transformation with empty domain, because this act has J2 as the apex. The element E acts as the identity, and the element S swaps the two elements of our act, so it swaps E and S. The second partial act has as the underlying set all cosets of S2 modulo S2, and there is only one coset, so that's a singleton act. All elements outside S2 act on this partial act as a transformation with empty domain, because we still have J2 as the apex, and both E and S act as the identity element on this singleton act. And this completes our solution. Problem 7. Consider the subsemigroup ION of all order-preserving elements in ISN. Prove that each transitive partial ION act is isomorphic to a cell act. Solution. Recall the following facts about ION. The two-sided cells, so J cells of ION, are in bijection with J cells of ISN, and this bijection is given by intersection. Then all H cells of ION are singletons. So let Q be a transitive partial ION act. Then it has an apex, so let JK be the apex of this act, Q. So JK is a set of all elements of rank K in ION. So here K is some number between 0 and n. For each subset X of the set 1, 2, and so on n, which we denote by n underlined as usual, of cardinality K, we have the corresponding idempotent epsilon X in ION, which is given by the identity transformation of X. Since epsilon X belongs to JK, by our assumption, the element epsilon X does not annihilate Q. In particular, there is an element U in Q, which is in the domain of epsilon X. But then, epsilon X times U is equal to epsilon X composed with epsilon X applied to U, which is epsilon X applied to U. And this means that epsilon X applied to U is a fixed point for epsilon X. Let us collect all fixed points for epsilon X in a subset and call it Q sub X. That's a non-empty subset, how we just established. If X and Y are two different subsets of n of cardinality K, then the cardinality of their intersection is strictly smaller than K. It should be smaller, not greater. And hence, their composition annihilates Q. And this implies that Qx intersection with Qy is empty. So now we can consider Q prime the union over all x of cardinality K of the corresponding subset Q sub x. Note that we just established that this union is disjoint, and all these Qx are not empty. Now let us consider the cell partial act Cx, which corresponds to the left cell Lx of epsilon x, so we fix some x. Let U be an element in Qx. Then, If we send an element alpha in our left cell Lx to alpha applied to U, this defines a homomorphism, which we denote by phi, of ion acts from our cell act Cx to Q. Indeed, if beta is an element in ion, then beta after alpha, where alpha is in Lx, is either in Lx or is strictly two-sided smaller than the apex, so it annihilates Q. Therefore, beta applied to alpha applied to U is beta after alpha applied to U, and both sides are defined simultaneously. The image of phi is a non-empty subset, and it is closed under the action of ion by this computation. So by the transitivity of Q, this image must coincide with Q. Our left cell Lx contains exactly n choose k elements because each element in this left cell has domain x, and the codomain is a subset of an underlined of cardinality k, and when we fix the codomain there is a unique element in ion because the order should be preserved, which sends this x to that codomain. So Lx has at most n choose k elements. Next, if alpha is an element of Lx with codomain y, then of course epsilon y after alpha is alpha. So in particular, alpha applied to U belongs to Q sub y. And this implies that the image of phi is contained in Q prime. And so, since the image of phi is the whole of Q, then Q is equal to Q prime. Our Q prime is a union of n choose k disjoint non-empty sets. And so the cardinality of Q prime is at least n choose k. And phi is a map, which is surjective and starts with a set of cardinality n choose k. This means that phi must also be injective and hence bijective. And this completes the proof. Some additional problems and questions at the end. Problem question 1. Construct explicitly all transitive partial T3 acts up to isomorphism. Problem question 2. Prove that transitive partial acts with apex J over a finite inverse semigroup S are in bijection with the conjugation classes of subgroups in the Schützenberger group of any H class in J. Problem question 3. Determine the number of isomorphism classes of transitive partial IS10 acts with apex J5. Problem question 4. If S is a subsemigroup of a semigroup T, then any T act is an S act by restriction. Is it possible, given some S act Q, to define on Q some structure of a T act such that the restriction back to S gives the original act Q? Problem question 5. Determine all pairwise non-isomorphic IS2 acts on a set with 5 elements. Thank you very much and see you next time.